So thank you everyone for being here. I would say just a few words about CyManII. So CyManII is a secure manufacturing institute. It's led by UTSA, and it's a large institute with a lot of different organizations from industry, from universities, and also from national labs. So this is I'm very excited of being a part of CyManII, and of course I'm very excited for being a part of the faculty at UTSA. Okay, so why do I talk about connected? Why do I say that everything is connected? Actually, if you look around, we are all connected. We all have our phones. Everything is really connected. Wherever we go, whatever systems we are talking about, whatever manufacturing system, whatever your homes are highly connected. So I've done work in different research areas, and today I just want to highlight interesting aspects that we discovered with our work, but also interesting aspects that would be interesting to consider moving forward for all our research, especially in the community here. So, for example, we are talking about cellular network, right? There are so many systems that rely on cellular networks. There are IoT systems. There are the car industry, right? Everything is moving towards connectivity, and they all rely on cellular networks. So then the reliability of cellular networks becomes key. And then we have all the different IoT systems for which we want security. But we want security and we want privacy at the same time. We want everything. And there are sometimes conflicting goals that we want to have for such systems, right? And when I'm talking about IoT, I'm talking about smart cities, smart cars, smart everything. We are moving towards an even more connected world, and we have so many interconnections between individual infrastructure, but across infrastructures. Again, cellular networks are supporting the IoT. Then we have IoBT. This is another area that I explored a few years back. That's a different kind of environment. Even if it's an internet of field, it's an internet of battlefield. So you have a particular type of interaction, and you have there is a different trust model when we talk about IoBT. So there are very interesting challenges there about trustworthiness. And then secure manufacturing. We are all, if you look around again, everybody has something that has been manufactured to some extent, and everybody has to rely and trust all the things that have been manufactured. So there is a very interesting area of building secure manufacturing systems on which we can trust the final product. And I'm going to talk a little bit about that towards the end of the talk. But again, I just want to highlight that the fact that all the systems are connected, that's the key thing that leads to security issues. And critical infrastructure is becoming more and more a target of attack. For example, in DHS in 2020, they were saying that there are a lot of spear phishing links to obtain initial access to IT networks, and then entering the OT networks, the other side, the operational sites. Then critical infrastructure again relies and can suffer degradations in performance, and then implicitly there is a cascading effect in other infrastructures that rely on them. And then let's not forget that every time we talk about critical infrastructure, we talk about cyber-physical systems. So it's not only, we cannot treat them in isolation. There is always an impact in the physical world that we have to keep in mind. So having all of these and reminding ourselves the connectivity, I'm going to highlight a few areas that I explored when talking about IoT security. So again, I explored the angles of connectivity. How can we identify devices and monitoring devices for anomaly detection? But again, this is an interesting aspect because there is the privacy angle as well. You want to monitor device, you want to know what's happening with a device in an IoT network, but at the same time, you can expose privacy, also the privacy of the person who might wear a particular IoT device. So then how can we? I also looked at ways in which we can model the cyber physical channels and attack paths that can happen within an IoT device, an IoT network. So imagine that you can actually, in a formal way, you can define how devices interact with each other, and by using verification techniques, you can also expose the unwanted channels of communication between devices. So that's another angle that is relevant, especially when we talk about cyber physical systems. And then causality, like everyone wants to understand how systems really work and how systems influence each other. And we talk a lot about correlations, but correlations are not that relevant in reality. What we really want is causality relationships between large IoT systems and systems in general, right? Even when we talk about enterprise networks, we have attacks in enterprise network, we want to show the causality relationships of an attack that is spreading throughout an enterprise network. And then I've done work where I was looking at the types of relationships in terms of commands over industrial control systems communication, and how those can expose, again, malicious commands and data sequences in those communications. So all of this work and all of the work where we are looking at interactions is actually again coming together towards this connectivity of IoT systems. And we saw that the connectivity actually opened up a lot of interesting doors for attackers. There have been, throughout the years, so many attacks, like from the ultrasound commands for Siri, Alexa, and Google, to the camera, to the toys that kids had to suffer through, and to the industrial pumps attack, where bubbles could actually damage the physical part of the pumps. So a lot of types of attacks. Sometimes, not all of them, going on connectivity. For example, the evil bubbles is not necessarily a connectivity, but in the end, the attacker has to have some access and some connectivity to a system. In some cases, physical. So I will just highlight some of the results in our work. So we've done. We wanted, with this work in particular, we wanted to see how can we determine if IoT devices have been exploited. How can we see that on different types of communication protocols, on Bluetooth, on Zigbee, or on Wi-Fi, and how can we determine that, and can we do it in a generalizable way? So this work was quite simple in a way, and cute. So we just looked at the types of the network traffic on all these three different communication channels: Zigbee, Bluetooth, and Wi-Fi. And we wanted to make sure that devices in an IoT setting, we had an IoT setting that resembles the home environment, and we wanted to make sure that devices are not changing their behavior, because that could mean that there is an attack. So the goal was to detect anomalies by observing clusters, and also by also considering where the devices are located. So by measuring this type of behaviors in the IoT networks, we were able to identify classes of devices. We were able to identify, for example, that we have multiple echoes. Even if they were different generations, they were behaving similarly. We have multiple sensors. Even if they were different generations, again, they were behaving similarly. And we also considered the physical properties of the devices by looking at the RSSI signal to understand the physical location of these devices. So we have the classes, but to be able to identify instances of those classes, we were looking at physical location. So we evaluated our work on 21 devices and on a data set that while we were working on this together with the interns, there was a new data set shared with the community in IEEE SMP, so we wanted to show that our method is general enough and applied the same techniques on that data set. And then we wanted to show that we are able to do anomaly detection, and we tried different approaches there. So just quickly, I will give you an idea of how our system looked like. So again, we were sniffing Zigbee, tapping into Android through Bluetooth, and we were also collecting the Wi-Fi traffic. And we extracted RSSI features with the direction estimation. And then we wanted to have the ability to identify the different types of devices that we had in the network. Then by using the location, we were able to say, hey, did something change in this network? Are my devices starting to behave differently? So that was the anomaly detection part. And then we had a way of displaying all that information. So in terms of the device type authentication, we looked at simple features. We looked at interpacket time, payload length, packet length, payload entropy, and packet entropy. And I know that these are, and then all the statistical values for that. And I know that these are simple features, but they were quite relevant when we talk about simple sensors and simple devices that we have in IoT, smart buildings, smart homes, and so forth. And by doing that, again, we identify the different types of devices, and then we also looked at the device direction identification to understand how and where those devices in the certain classes are located in a system. And again, by using the RSSI signal, this didn't require sophisticated techniques or new types of hardware to understand better the location, and we were able to identify the location of the devices. And in terms of the anomaly detection, again, all these devices were clustered. We had different clusters, different centroids for each individual device, and we were able to determine when a device would change its behavior. So let's say that our evaluation wanted to answer the following. Is our clustering technique able to cluster different devices? Is it generalizable? Can we apply it to other data sets? Can we detect the direction of where the devices are located in a physical space? And can we do anomaly detection on all of this? So we didn't need too much traffic actually to extract these behaviors. So for example, for 7 hours we collected Wi-Fi traffic, and we were able to achieve very high accuracy for clustering the different classes of devices that we had in our network. And similarly, we applied the same technique for Zigbee and Bluetooth. And all of these were the classes that we discovered. And these are, for example, these are the clustering performance for all the different types of devices for the iPhone, homemade, smart plug, and so forth. So these are the performance metrics that we discovered for all of them. And again, we didn't need too much traffic data because all these devices have a pretty simplistic behavior in a way. And then we followed with the second data set from IEEE SMP paper, and we were able to achieve similar numbers also for their set of devices. So this is just shows us that even with simplistic features, we can actually determine very easily what's happening in a network, in an IoT network, with respect to sensors and simple actuators. And then we looked again at we evaluated the device direction identification, and we were able to actually test our approach in two different setups. One in our setup in the office, and we actually set up a second similar test bed to see if our approach holds, and we had a very good result in that respect as well. So we had accuracy of 95 and 85 for 4 directions. So we are not, the method is not as good as at finding 8 directions. So the accuracy was decreasing because the RSSI signal is not as strong, and it doesn't give us enough information when we looked at 8 directions, but it was pretty good for 4 directions. And then we follow through with different anomaly detection scenarios where first we just use different protocols. We use the cryptocurrency miner, so these are more obvious types of anomalies, but we also had an IRC bot on some devices, and we were able to detect those. And again, these were the different clustering, the different clusters for the different types of devices. Every time one of these attacks would show up, the clusters would change their shape and indicate that there was an anomaly. So this was a paper that got the Best Paper Award in the IoT conference in 2020. But I think that its value is also to show that sometimes simple features can give us a good indication of what's happening within a network, and for certain types of devices. This will not work for much more complex types of interactions. It would not work in a enterprise network scenario where you have much more variability and the behaviors are much more complex. So again, looking at all these connections, looking at all these connectivities, and looking at how devices interact with each other, enable us to identify these types of sensors or all sorts of IoT devices, and also allowed us to do direction estimation and know where they are placed in a particular physical space. But this comes with a drawback on privacy, right? What if we are talking about devices that are attached to humans and we don't want to reveal that information? So we always have to have this type of trade-offs where, yes, we want a network where everything is monitored, and we want to know for sure that our devices are secure, but at the same time we don't want to leak anything about the privacy of the users in that environment. So that's an angle that we didn't consider in this work, but I think it's also relevant to see to what extent can we say which devices are actually revealing anything about the humans in the area. So that would be a nice extension to it. Then in terms of cellular networks, I've done some work for 4 years. We collaborated with Nokia Research, and we had a lot of different angles in analyzing cellular networks from a reliability perspective. So we were looking at the health of cellular networks. How can we determine if cells in particular have abnormal behavior? How can we not only detect but also diagnose a particular network? How can we, when changes are made into a cellular network, we were working with LTE. I want to emphasize that this is older work. We were focusing on LTE, not 5G. And we were also looking at ways in which particular changes that are made across the whole cellular network would have a negative impact. That's something very relevant. And if we think about it, that would be even more relevant in the setting of digital twins. So ideally, you don't want to push a network change. Ideally, you want to test it ahead of time. So our techniques should have been even more, let's say, robust if we could do them without assuming that changes have been made to the network and then observing if the network is going into a strange state. And then one other interesting topic that we were also looking into is whenever we set up a new system, we don't have a behavior of that system. We don't know how the system should interact. So if you have a new network, how can you transfer the knowledge that you have from other networks to this new network so that you understand if the network is behaving normally? So that was another angle that we were looking at. And again, it's a matter of understanding these connectivities between between cells and how certain areas might influence the overall behavior of, and I'm talking about physical, geographical areas, might be influenced by weather-related events and so forth. So this work again, I want to highlight the fact that we are moving towards private cellular networks. We are moving towards smart airports. We are moving towards 4G cellular networks on the moon. So having the ability to say something about reliability of these networks and also security of these networks is key in so many new scenarios nowadays. And then the supply chain is another beast, which I'm going to talk about a little bit later. So just to highlight a few ideas that we had throughout this work, and again, this was done a few years back, but we were operating in we didn't have any labels, so non-label setup. We had access to these key performance indicators for every cell in a particular network, and we were trying to figure out, is this cell healthy or not? So again, all these systems are highly dynamic. Operations change over time. There are different parameters that are changed. There are different configurations that are changed, and so forth. The users also have an impact. The volume of users that are attached to certain cells is also has an impact. So we had to come up with this was the first attempt to analyze that data, and we came up with a very with an approach that was trying to characterize every cell based on these key performance indicators. We tried different models, and we continuously updated these KPI models just because, again, there is this dynamic aspect to the networks. And we employed an ensemble method approach that was giving us the ability to understand what's the performance of all the different models in our ensemble, but also we had some extra information. We have these configuration management changes, so we had a way of understanding when something was supposed to happen in the system. We didn't have necessarily labels, but we had this context information, the configuration management information. So the first experiments were only on 70 cells that we had access to, 12 KPIs, and again, no ground truth data. We worked with subject matter experts to understand how we could label the data so that we can verify our results. We used all this contextual information that I was talking about to understand when changes happen in the models and how to age out models and so forth. And we were able to reach some very, very good results overall in terms of the average detection rate and the false positive rate. So these were the different types of univariate and multivariate approaches that we took. And again, we had decent results. And we continued the work, and we looked into this idea of zone coordination or verification. So this idea of making a change throughout the whole network, see if the network changes behavior or not. Again, all of these are related to this concept of connectivity, because all these cells are working together to provide a particular service, and they are configured in such a way. So with this zone verification idea, we wanted to do not only detection but also diagnosis. So we were inspired by one concept that a lot of people are using in NLP, topic modeling. And we wanted to see what are the topics in a particular cellular network. What kind of states do you have normally in a network? So we were able to discover these topics or states in cellular networks with respect to these key performance indicators. So the network will have a mixture of key performance indicator behaviors in all these different states that we were discovering. And we had a way of interpreting that. What was nice, we didn't have labels, but you can actually interpret, and we had a way of interpreting the states based on the actual characteristics of the key performance indicators, because we had drop call rate. So we know that a very good drop call rate means that you don't have drop call rate, right? So we had a way of automatically inferring if some KPI state is bad or good. And by doing that, in the detection mode, by discovering all these different topics, all these different states in which the network was, and having a way of interpreting those states, we were able to also say whenever the network would be in a bad or good state. And more than that, we wanted the diagnosis. We wanted to understand why all of that was happening. So we used the Markov logic networks, which are very easy to express as first order logic. So you express certain rules, and then you get the most likely explanation for a particular state. So we did that. We combined topic modeling and MLNs to understand how certain states of a network were how to diagnose them. So when I'm talking about diagnosis, we wanted to understand again if certain configuration management in the network were having a bad influence. So if we could see that there was a relationship between the configuration management changes and the state of the network becoming bad, then we knew that those configuration management changes would be the reason for the degradation of the network. So we had data for 3 months from 9,000 cells. This time the data set was much larger. Of course, whenever you have real data, you have missing data points, so we had to make up for those. Again, no ground truth, but we had information on the configuration management. We had the information, and we had a way of interpreting the different key performance indicators because they are self-descriptive in a way. Okay, so once we analyzed our network with 9,000 cells, we discovered 32 topics, 15 normal and 17 abnormal. So we could distinguish between all of these different states. And this is an example of an abnormal state where most of the cells exhibit a call success rate that is not that great. It's actually a degrading call success rate. And in different phases of the communication, those are different KPIs that are defining different phases of the communication. So by doing that, then we were able to identify what cells are influenced by certain configuration management changes. And actually, configuration management change is actually changing the angle of the cell. If you change the angle of the cell too much, then you can change the key performance. People might not be able to access the cell if they are in between cells and you change the angle and they don't have coverage for that particular area. So this was a very interesting result that actually show us that we have a way of identifying and diagnosing system even when we don't have labels, and that's the key thing. And then one other thing. So this is another way of showing the results on the angle. We also looked at weather and see if the weather in the area where the cells were located had also an impact with respect to the performance of the cells, and we found similar. We found certain events in the weather that actually led to degradation in performance. So all of this was quite interesting work. And again, we were relying on information from the cellular networks to understand its performance. But think about attacks also. If we have attacks and we have this type of key performance indicators, we can also detect in the same way potential attacks on cellular networks in a similar way. So this was just this was work that was exposing problems due to configuration changes or weather-related changes, but in the same way we could detect attacks. Okay, so let's see. What about secure manufacturing? So I've been showing all these different angles on IoT devices and on cellular networks. But now we are talking about secure manufacturing. We are talking about supply chains. We are tackling a completely different new era, because the supply chains nowadays are hard to be tracked. We don't have instrumentation. We are moving towards digitization of manufacturing systems. But can you tell me where all the chips on your phone came from, and if they were tested, if you have any way of really trusting your phone? Probably not. None of us can, right? So that's one of the keys that we are looking into for secure manufacturing systems. But I would say that there is now a good time to think about formal design specifications when we are building new types of systems. So even for IoT devices, even for 5G, we can look in ways in which we can formally define systems and do that at the design time when it's the cheapest to understand and remove any potential attacks or any potential reliability issues. Both of them are equally important. And then, again, going back to the phone and to the fact that none of us knows exactly what's happening in our phones in reality, in terms of the hardware that we have, having a way of extracting provenance information and being able to say, to see all the information about our phones and have some guarantees with respect to how a particular part is manufactured is key. And then with the pandemic, we also saw that we need to be prepared for pandemic adaptive supply chains, right? Everyone noticed that, and now we have other types of supply chain issues as well. The baby formula is the newest one on the list. So there are so many different ways in which we can use certain lessons that we've learned throughout the years to actually be able to have processes that are verified and processes that are monitored. And funny enough, biopharma systems are targeted more and more in terms of attacks, and they lack a lot of the security mechanisms, and they lack actually the ability to collect provenance information. Even if we know that every vaccine that we all took had a particular batch, so we can go to the batch, we can go to information like that. But when we talk in general about biopharma, we lack the security mechanisms, and biopharma brings another angle that is very strange, the fact that we have a stochastic nature of the living system. So these are different challenges that we don't necessarily have for other types of manufacturing systems. But again, this provenance information is missing, and it's missing across multiple manufacturing areas. So we have a paper that was just accepted at IEEE S&P magazine, where we talk about this concept of a pandemic adaptive biomanufacturing. And the pandemic aspect is obvious at this point after 2 years in the pandemic. But then even if we have capabilities of building automated secure manufacturing systems where you can adapt and accommodate new types of products, you also have to allow users, you still have humans, you have to allow accessible and usable usability of the authorized users. And then we have to think about all these aspects of resilient and security manufacturing systems. And again, connectivity is the key part, because we want to make sure that we build systems for which we have strong security guarantees. And last but not least, of course, there is an economical angle. We always have to have systems that are relatively cheap, so that small and medium-sized manufacturers can also employ. So let's think a little bit more about the manufacturing. What did we learn from this pandemic? We learned that it's never good to have products and to have stockpile of fully flashed products. We saw that with the ventilators. We saw that with a lot of different areas. So ideally, when we build the future types of supply chains, we want to make sure that we have raw materials in stockpiles, so that it's easy to put together and to orchestrate infrastructures that can easily allow us to build products in a very pandemic efficient way. So just imagine the following. I think in around 50,000 companies have their supply chain, the tier 1 supply chain, coming from the Wuhan area. And then the second level supply chain, actually there are 5 million companies that are the second tier, have the second tier supply chains coming from the same area. So this is a problem, right? If a particular geographical area has a particular issue, we cannot rely on those. We have to diversify the supply chain. And then digital inventory is another thing that is very relevant when we talk about supply chain. So we have to have the ability to have the designs, to have everything accessible, right? And everything secured, and everything ready to be shared with the parties that could start producing the different parts. So we have to have digital inventory designs, data, and templates so that we can easily scale up a manufacturing system. So again, this is not an easy task, and it requires a lot of interactions and connections between the different factories, the different stockpiles, and the critical facilities in which all these products would need to be put together. So imagine how complex these networks should have to be, right? Imagine how what types of communication do we have to have in place? How quickly we need to act in such scenarios. The technical expertise is another thing that needs to be handy. And then let's switch to the digital ecosystem. So in order to be able to achieve these pandemic effective capabilities, we need to have digitization, and we need to have techniques in which we can, again, collect all the information. We have this concept inside CyManII of a digital passport. So imagine that for everything that happens within the manufacturing process, we capture the state of the machines that were operating and that were producing different parts. We have hardware and software traceability. We have all the different characteristics of the products that are generated in the manufacturing process. But we are relying on sensors, like we were talking about earlier, right? To collect all this information, we have to have sensors that we trust. And that's a very important part, and we need to be able to have ways in which we can remove certain security issues at the design time, but also have monitoring capabilities at the operational time, so that we can say something about the health of those sensors. And digital twin can also be very, very important here if we have the ability to build digital twins for not only manufacturing systems, but IoT systems in general. Then again, we know when changes happen. We were talking about Tesla earlier, right? I wonder if they have anything like that behind the scenes, if they have the concept of a digital twin before they push any of their changes. Do they have a way of verifying that they are not going to impact negatively the performance of the cars? So all of these are needed. Otherwise, we cannot have reliability in systems like that. And if we can prevent, I think prevention has to be our future. How can we prevent? Can we use formalism? Can we use prediction? Can we use prediction mechanisms? Can we use these digital twins to tell us if something will go wrong? All of these are key for the future. Because they give us the ability to prevent. If we detect, it's a little bit too late, unless we have other mechanisms that constrain the effects of attacks, instead of having cascading effects. Maybe you can constrain the effects, and you detect it within a particular smaller set of your system, and then you have resilient systems that can address the failures. But anyhow, I think we have to think more in terms of prevention. And we know whenever these systems are built, we know there is a particular intent of the systems. We can model the intent. We can model we can model even we were talking also earlier, we can model even the control systems, and we can understand when they start to exceed the safety envelope, let's say. So there are all of these techniques. I think as a community we have to explore them and come up with stronger guarantees in terms of security. So I think, where does the future take us? There is no one infrastructure. I think there are only we cannot talk about one infrastructure. All of them are connected. If we are connected via the internet, we are connected somehow across different infrastructures, and we need security across all of them in a way, or we need a way of understanding these interconnections between the connected infrastructures. Ideally, we should have security guarantees from design, implementation, and deployment, and then there is this transparency and explainability, right? We want transparent systems. We want to understand what's happening in the system. We want to explain what's happening in the system. We want to explain when a particular attack, how that happened. We need these properties in our systems. But then privacy and transparency need to also coexist. And I think that's a challenge because sometimes, this is probably harder to achieve in some cases. If you want full transparency, how do you do that when you have privacy constraints? So yes, we have to explore privacy preserving mechanisms, and we have to have them at a scale that is needed for very large systems. So I think these are the future challenges that we are all going to face, and it would be nice to have some answers in the next years. Okay, I'll stop here, and I would love to have more discussions. Thank you.
Any question? Be good if you identify yourself.
I'm Edward Knightley from Rice University. Thank you for the very interesting presentation. I have a question for you about the first part, anomaly detection, and especially, well, maybe both Internet of Things and cellular. And what are your thoughts on how we differentiate maybe from flash crowds or other events that would change kind of the mean operating point? Do you call all those things anomalies, or are you trying to differentiate from those other rapid changes? That's
an excellent question. Thank you. That is always an interesting question. And I think having extra context information can give us more abilities to distinguish between the different changes. For example, when we talk about industrial control systems, there are different modes of operation. So we need to be aware of those, and we need to be aware of a system going into a maintenance state, right, or into a different state. Yes, I think just doing anomaly detection blindly will not take us to where we need to be. I think we need to try to understand this extra context for all the systems, so that we understand better causality. I've been mentioning causality. We need to understand the causality of the anomalies to be able to have a stronger system.
Okay, thank you.
Thank you.
I have a quick question about that. So, was the data from the single tackle, or was from multiple?
It was from one. So it was one network. Yes. That would have been nice. I later on in other papers, I had a lot of papers there. We had data from different networks in different geographical areas, and there were some similarities between them, but you have a good point. If it's from the same...
Because, so this is my just comment. We actually had a measurement data from 28 tackles globally. It was our paper in 2018, and basically we compare the control plane operations.
Mm-hmm.
And for example, like US AT&T is the worst in terms of performance.
Okay.
And when you go to Korea, I mean, your first setup time in the US was like 3 seconds or 5 seconds. Korea was like 0.5 seconds. I mean, so the quality of the cellular network is so different.
Across.
I'm not sure whether those like higher level KPI.
I think I mean they are important within the same operator. Right? They are important for the same operator. So I guess you have to have a different interpretation for other operators.
So another point we also made in the paper is that because the telcos never compare against others. They just worry about their measurement. So they have a tunnel view about their system. And usually you use just the one telco. So you don't know how good yours compared to others because you cannot compare. And I think this is exactly the problem of the cellular, manufacturers. And they know that actually they should have compared against, different telcos. Then actually it may show some cases good data, some cases bad data.
Yeah. Well, my collaborators were willing to publish all this data, and we were talking about it in different events. But I can see if there is no standard way of measuring the performance, it's a little bit difficult to have this comparison across operators. But I have to tell you that when we were playing with this idea of transferring knowledge from one network to a newly set up network, that definitely worked for the same operator. Probably it wouldn't have worked across different operators, but for sure you could actually transfer information from a given network for which we had all these models. And when we tried the same models in a newly set up network, they worked for the same operator.
Thank you for this amazing presentation.
Excited for yourself.
So my question is related to classifying the IoT devices that you have mentioned. So if you could expand it a bit more, because did you classify it based on the functionalities of the devices or the types of data that has been collected?
I was mentioning that the features were they were network features. Just a second. So we were just looking at those features to be able to identify the different classes. And when we, one second, where are they? Here, interpacket time. So very simplistic network-based features were actually giving us a lot of information about the different classes of sensors. And I guess they are also very vendor specific in a way, because they are very vendor specific. They use the same stacks and whatever. So then you can extract these behaviors. But that also tells us that we can use these simple statistics to figure out when something goes wrong in these networks, and why don't we do it? Yeah.
Thank you.
Follow on to that, and then I have another question. But we have a paper at WiSec called Home Stitch a couple of years ago where we go individual behaviors within devices, and exactly what you said, like D-Link devices look like D-Link devices.
Yeah.
So within then you can differentiate, but the stacks are so similar. So at the end you were talking about a lot of motivation for provenance. Right? When I think about provenance, I think about more of the detection side, kind of figuring out what happened, what could have happened. But then you kind of had this call for prevention, right? And I think there's actually an opportunity for these to kind of come together in a way. And I think I was following your train of thought there, and I was wondering if you could expand on that a little bit.
Yeah. So prevention allows us to build systems. Right? Okay. If I start again from the formalism allows us to build systems which are cleanly defined. You have the interfaces between the different components that are talking to each other. You can change the abstraction layer at which you want to define security properties and so forth. Right? If we are talking about the micro or the macro levels of this high infrastructure, that's one thing. Then we have prevention, but then we also need, with the prevention, with the formalism at the beginning, we can reduce certain classes of attacks. But we all know that will not mean that we reduce everything. However, if we do it early on, it's much more cost effective. Then later on, we also have to have monitoring capabilities that enable us to understand even more if the systems are functioning correctly or not. But we have to have ways, whenever we do this detection, right, we have to have ways in which we can either constrain the effects of what's happening in the system, of the attack, or we have to have a way of predicting. So not getting to the detection, but actually preventing for the full attack to be finalized. So provenance can give us that information. For example, for a manufacturing system, we can look at the geometry of the part that is being produced. And when you see that the geometry is starting to deviate from the normal from the golden standard that you can have for a part, then you know that something is happening in the system. So you will not take that part and move it to the next level in the supply chain and propagate an attack or a fault throughout the supply chain. So you can stop it and you can prevent it before it gets too late, before it gets into a plane or who knows where, right?
I guess one of the big challenges with provenance is knowing what do you want to record, right? What are the features that you eventually want to write policies about on that, and how do we discover those in the first place?
So I think those are discovered together with SMEs and people who are working very closely to different machines, and they have already a sense for the different types of sensors that are needed. And in our discussions with a lot of industry partners, there is no formal, definition of what those are. And I think it's important to discover them and capture that information. But we all know about SBOM, right? SBOM is now is a work is more than in progress. It's been evolving a lot in the past years. And I think there we immediately see the value of being able to track down the software that goes across the supply chain and so forth. The same kind of idea, we have to do it for hardware, right? We need to understand what's happening with respect to the hardware that is used in the different manufacturing machines. And the same idea has to go with respect to the context in which a part has been built, because the context tells you the health of a part as well, right? What happened on the machine? What is the geometry? What is the energy consumption? We look at energy from two perspectives. Energy is important because you want to be energy efficient when you do manufacturing, but also energy can give us some very interesting indications in terms of security. So if you see that your energy patterns change, there could be a potential. That can be a...
So it's interesting that you kind of moved to the SBOM there, because conversations I hear about SBOM is, well, it's nice, but what is it really giving us? It's not actually giving us the information we want about the vulnerability state. It's just a kind of, we have to do this sort of thing, which kind of gets at that root of what is the information we actually want to get at in these different domains, right? And so SBOMs really want to get vulnerability information, which isn't quite there. In this space with the hardware, what is it that it just sort of goes back to the question of what do we actually want to be recording in the provenance?
Okay, so so specifically for manufacturing, you want to understand if the part that you got actually matches the design. That's what you want, right? You have a design and you want to make sure that at the end of the manufacturing process, you have a match between the design and the part. And every manufacturing sector will have different types of machines involved and will have different ways in which they can qualify what is the quality of a part. If we're talking about a CNC machine, again, geometry is key, because you have the design and you have to make sure that the geometry of the part that comes out matches the design in terms of the geometry, and not only the geometry, also the material characteristics as well. So you have to have the correct mass distribution, for example, and so forth. There are so many interesting aspects to look into.
Yeah, so that's the belabor of it. Yeah, anyway.
Yes, thank you.
In terms of testing, because I work on cellular, I know cellular testing. And so when you look at the cellular standard, there is a conformance test suite that mostly checks good messages.
Yeah.
Good messages are handled correctly. So So you may be able to test whether good messages are handled correctly. But I think one thing we found is that because the specification does not deal with the negative cases,
Exactly.
like violating cases, right? Can you actually systematically build like a good set of violating cases that if those violating cases are handled correctly, like exception handling is done carefully? I mean, there is no such standard.
No.
And that's why there are a lot of bugs. I mean, they are not handling the exceptions correctly. And I think in terms of for example, manufacturing machines, I don't think there is a good design. Right? The design should have actually no bugs. Right? And then finding bug-free design itself is difficult. Once you have a design, then you need to have a testing.
Sure.
Right? And if you do not have good design, I mean, probably they don't have any formal verification for the design. And then there is no testing. So you cannot guarantee any like a correctness or anything, right?
There are testing even now, but what if from the design to the actual hitting the machine, somebody interfered and suddenly the design was correct, but somebody changed the G code that is running on the CNC machine, somewhere in the middle, and then on the machine you have an incorrect G code. The part that is manufactured will not match the design at that point. So there are all these different points on the manufacturing pipeline that needs to be verified so that you know that the integrity of the design is maintained, but that integrity changes its shape. It starts from a file of a design, but then it becomes a G code, then it becomes the actual geometry of the part and so forth.
And that's sort of what you do with the broken cellular, where you take that and apply it to the last piece and say, here's the recordings information out and say, here's the thing that actually matters.
Yes.
Generically making the policy very, very difficult.
Yes, yes. And we want to remove the manual part. Yeah.
Any other questions? It's exactly 10 a.m.
Okay. Thank you all.
Thanks again for the speaker. And actually, we have a present and something for her. And
Thank you
this
so
is
much.
Certificate of Appreciation, ACM WiSec 2022. It's presented to Gabriela Ciocarlie.
Thank you so much.
Right? And also, I guess, present from
Thank
the
you. Appreciate it. Thank you.